velocity and other rates of changes, followed by 3.5 derivatives of trig, and that'll finish up chapter 3. Okay, so listen where we are. So let's see. Okay, so 3.4, instantaneous rates of change. Okay, instantaneous rate of change. If you go to page 129 in the middle, there is a definition where f prime of a is equal to limit as h goes to 0, h over f of a plus h minus f of a. Okay, you already know this, have used this many times. Okay, so let's go ahead and see if we can do example number 1. In example number 1, it says, find the rate of change of area A of a circle with respect to its radius. So first of all, if we want to find that, we need to find the relationship between the A and, so the area and the radius, right? A as a function of R. So A as a function of R is nothing more than pi r squared in a circle, right? And A tells us find the rate of change of A. So it'll be A prime. So in other words, or dA dr, right? dA dr, or A prime of R. So we'll take the derivative of this with regard to R. So you have R squared, so the 2 comes forward and it becomes 2 pi r. And that's it. Nothing more than that, right? B, evaluate the rate of change of A when R is equal to 5 and R is equal to 10. So when R is equal to 5, I put R is equal to 5 here, and it is 10 pi. When R is equal to 10, I get 20 pi. Okay, not too hard. C, if R is measured in inches and A is measured in square inches, what would the units be of dA dr be? So dA dr would be square inches per inches, right? It'd be square inches per inch, I'm sorry, right? Okay, so that's not something you can cancel the inches out, right? We already talked about this. This is not a dA over dr thing, right? This is just a nomenclature, dA dr, okay? It is inches, so the inches squared, how the area changes as the radius changes, okay? All right, go to page 130, and in page 130, we are going to have motion along a line. Motion along a line, okay? Motion along a line, so we're gonna call S the displacement, and it is gonna follow some sort of function with regard to time. So as time goes by, the displacement will change, okay? So what do we know here? We know that the velocity, okay, the velocity is equal to ds dt. Or in other words, S prime, which here would be F prime t, right? So if I take the derivative, the rate of change of displacement is velocity, okay? Can anybody tell me what the rate of change of velocity is? What do I use? What word do I use to describe how fast or how slow the speed is changing, or the velocity is changing?
Acceleration.
Acceleration, A, right? It's the acceleration, okay? So acceleration is dv dt or v prime, which is basically f double prime t, right? I'm taking the derivative. I took the derivative here once, and I'm taking it again. Okay, so if you go to the bottom of page 130, it gives you the instantaneous velocity. The velocity is ds dt right here, or s prime. Okay, whereas the speed, okay, now there's something called speed. Velocity and speed are, velocity has a direction, whereas speed does not have a direction, okay? So if I'm speeding at 60 miles per hour, That's all I'm doing. I'm going at a rate of change of 60, but I don't know where I'm going, okay? It does, because it does not have a direction. I could be going to Salem, I could be going to Eugene, I can go to Lebanon, wherever it is, okay? So it's different. I don't think the speed does not have a direction part to it, okay? So if you look at at page 131, at the bottom part, it says that speed is the absolute or the magnitude, the absolute value of velocity, okay? So let's go to example number 2. Example number 2 says figure 3.24 shows a time to distance graph of a 1996 Riley and Scott Olds race car. The slope of the secant PQ is the average velocity for the 3-second interval from 2 to 5. In this case, about 100 feet per second, right? And you can see the elapsed time is 3 seconds, and it traveled about from 50 to 350, so about 300 feet. So in other words, it is about 100 feet per second, okay? Slope of the tangent P is the speedometer reading at 2 at about 57 feet per second or 39 miles per hour. The acceleration for the period is shown as constant 28.5 during each second, which is about 0.89 G. G is gravity, right? The constant of gravity. Okay. So let's go to example number 3. It says reading the velocity graph, reading the velocity graph. A student walks around in front of a motion detector and records her velocity at 1 second intervals for 36 seconds. Okay, she stores the data in her graphing calculator and uses it to generate the time velocity graph shown in 3.25. Describe her motion as a function of time by reading the velocity graph. Okay, so let's go ahead and do this one. This one's a little more interesting. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 ticks there, 9 ticks, right? And each, and 9 ticks, and that's going to be the 36 seconds. So each tick is approximately how long? Anybody?
Four seconds.
4 seconds, right? Each tick is about 4 seconds. Okay, so there's a tick here. Looks like there's a tick here. One here. One here. On the bottom, our bottom's out there. One there. Oops. One here. And then one about here and one here. 1, 2, 3, 4, 5, 6, 7, 8. Well, I'm missing one. Okay, looks good. Okay, all right. So what's happening? This is a what? This is the student's velocity. So this is the velocity. Okay, so the velocity, and this is as time goes by. So as time goes by, I am going, velocity is positive, correct? So we're going to go ahead and let's define positive as being to the right. Okay, so we're going to say positive is to the right and negative is to the left. Okay? So it's going to go positive, positive going to the right, and what happens here? So it's going to go faster and faster and faster because the velocity is going up, right? Which means that what are we doing here at this point? What do I say when the velocity continues to increase? What am I doing?
Accelerating.
I'm accelerating, right? I'm accelerating to the point here, and then from here to here, what's happening? My velocity is constant, right? So I'm going straight. I'm going at a constant speed here. Constant velocity, which means that the acceleration is what?
Nothing.
0, right? I have no acceleration. because I'm going at constant positive speed, right? And then I'm going down here. What am I doing here? What's happening here? Velocity is going down, which means that I am decelerating, right? Till I come to a point where my velocity is 0, and then it goes negative. Velocity being negative means what? I was going to the right, now I'm going to the left, right? So I'm going negative here. All everything now is negative, right? You know, negative faster and faster in the negative direction, right? And then kind of slowing down, but still going in the negative direction. Then what happens here? And here my velocity is?
Nothing. 0.
It's 0, right? Which means that I am at a what?
Stop.
I'm at a stop, right? I stopped. So I stopped from here to here. Then I accelerated back to in the which direction, right or left?
Right.
To the right, right? Because velocity is positive, okay? So let's see what it says. Oh, so it doesn't say anything. What does it say here? It says the student moves forward from the first 14 seconds. So we're going forward here, right? And then moves backwards for the next 12 seconds, stands still for 6 seconds, then moves forward again. Okay? All right, so that's that. So where's my maximum speed here? Can anybody tell me where my maximum speed is? What was speed?
5.
Huh?
Yeah, 5.
Wouldn't it be like the tallest one, even if it's negative, because it's absolute?
Correct. So it's the highest peak or the lowest valley, right? Because this here is a certain speed, but this guy here is going down negative more, so the actual speed will be larger here because the magnitude of this peak, the bottom peak, is larger than this peak. Okay, so this point down here would be the maximum speed. Okay. All right, go to page 132. There is acceleration. We already talked about this. Acceleration is dv dt, or the double derivative of s, right? Okay, so then we're going to talk about free fall constants. Free fall constants, okay? So in free fall, if you look at page 132 in the middle, there's a green box there. These are equations that you've already learned before. So you know this, right? You know that in a free fall, the displacement is 1/2 gt squared, right? Or in other words, if you're looking at feet, right, this is going to be what? 1/2 32t squared, okay? But if I am here, okay, and I call this point 0, and I drop it and free fall this way, I'm just gonna go ahead and let it go. Okay, I'm gonna go ahead and let it go here. If I let it go, which direction is G? If this is positive, if this is 0, and this is positive, it's going down negative, right? So this actually 32 is negative 32 because it's going downward, right? So this is the same as negative 16t squared. And you guys have seen this before, okay? So if this is that, what is the velocity? Velocity is nothing more than s prime. So I can take the derivative of this, what do I get? Negative 32t, right? Because the 2 comes down, becomes 2 times 16 is 32, and then I just, instead of t squared, now I have t. Right? What's the acceleration? Acceleration is the double prime of s. So you take the derivative of this, t to the first, right? So it just becomes negative 32. Correct? And that is shown there, well, not shown there, never mind. Okay, so let's do example number 4. Let's see if we can use this, some of this in example number 4. Modeling vertical motion. A dynamite blast propels a heavy rock straight up with a velocity, launch velocity of 160 feet per second, about where it reaches a height of that after t seconds. So I have this, and it's going to go up, and it's going to come back down like that. Okay, but the S is going to be given to you as 160 t minus 16 t squared, minus 16 t squared. Okay, so A, how high does the rock go? So how high does it go? Okay, so how high does it go? And then it comes back down, right? So anybody want to guess how high it goes? What happens when it's at its peak? Right here. What's happening here? What is my tangent line like? Isn't my tangent line going to be 0? Right?
Yeah.
So the slope of the tangent line is going to be equal to 0. So if I take S prime, I get 160 minus 32t. If I set this equal to 0, I get 160 is equal to 32t. T is equal to 160 divided by 32. 5 seconds. So it takes 5 seconds to get top, then 5 seconds to come back down, right? That was A. Oh no, how high does the rock go? So T is equal to 5, so I plug in T equals 5 here. You get 160 times 5 minus 16 times 25. What do I get here? I get 900 minus 400. Looks like it's 500. 500, is that the answer? Oh, it's
400.
400. Oh, this is 500. 500, so this is going to be 400. Okay. B, what is the velocity and speed of the rock when it is 256 feet above the ground on the way up and on the way down? Okay, so the maximum height was 400. We found that out. This is 400. Okay, so it's going to go 256, which is somewhere around here, I'm going to guess. So I want to know, what do I want to know? The velocity and velocity when that goes up. So first of all, I have to find out what the time is, right? At what time is it 256? So how I do that? I would put 160t, let's just do it here. My height is going to be 160t minus 16t squared, and I would set that to 256. If I move them over, I get 16t squared minus 160t plus 256 is equal to 0. It looks like everything's divisible by 16. T squared minus 10t plus, this would be 16, right? It's equal to 0. So this is going to be t minus 8. T minus 2 is equal to 0. So t is equal to 2 or 8. So it's going to go at 2. It's going to be at 256 at time t equals to 2. And then go at t equals 5 is going to reach its height. And then 3 seconds later at t equals 8, it's going to come down and achieve this again, which kind of makes sense, right? In other words, it takes 2 seconds to go from here to here, 3 seconds to go from here to here. So when it takes 3 seconds back to drop back down here, and then another 2 seconds to drop all the way back down, right? So B, what is the velocity of the rock. So the velocity of the rock is what? So the velocity was S prime. So S prime was this prime. So it'd be 160 minus 32t. So t is equal to 2. I put 2 in there. I get 64. So I'm going to get 96. When t is equal to 8, what do I get here? I get 32 times 8, 16, 1, 256. So 106 minus 256, so I'm going to get minus 96, which makes sense, right? Because 96 going up, 96 coming down, right? So when it's going up, the velocity is positive. When it's coming down, the velocity is negative. Okay? C, what is the acceleration of the rock at any time during the t? So at any time, the velocity was this. So the acceleration is v prime. So it's this prime. This goes away because it's just a constant. It's going to be negative 32. So which makes sense, right? What it's saying is that the acceleration is always going to be negative 32 because the gravity is always working on the object. So that's why the negative 32 is constant throughout the entire time. D, when does a rock hit the ground? So it takes 5 seconds to go up, 5 seconds to come down, so it'll be 10 seconds. Okay? Let's stop right here, and then we'll continue on later. So we're going to stop right here.